and resonance is the first one that we're going to cover. So this question, what are the respective hybridizations of the atoms numbered 1 through 4 in this compound? Does anybody know how to do this question?
I remember hearing count things such as the triple bond count 1 is one thing, each double bond count is one thing, each single bond count is one, each lone pair.
Exactly, yeah. So basically, each single bond, double bond, and triple bond count as 1, and then each lone pair you also count as 1, and then you just subtract 1. So what I mean by that is if you look on nitrogen, you have 3 single bonds and then 1 lone pair, right? So then it's sp3 hybridized because it's 4 minus 1 is 3. So then the next one, if we look at carbon, it has 2 single bonds and 1 double bond, right? So then 3 minus 1 is 2, so it's sp2. And then carbon number 3 has 2 single bonds and then also 2 single bonds for both of those hydrogens, right? So it has 4. So then 4 minus 1 is 3, so number 3 is sp3 hybridized. And then carbon number 4 has a triple bond, so you only have 2, and then you minus 1 and you get just sp hybridized. So you might have these memorized by now, but if not, that's the way that you learned how to do it in Orgo 1, or at least that's the way I learned how to do it in Orgo 1. So you'll probably get a question kind of like that, which is nice. Any questions on it? So it was D. Okay. Okay, so this is an aromatics question. So which structures would be classified as aromatic? Do you guys remember what you need to be classified as aromatic? Yeah, so you need planar. Okay, so there's a couple things. So you need a 4n plus 2 rule. Conjugated, planar, conjugated. Anything else? Cyclic. Mm-hmm. I think that's it, right? Okay, so 4n plus 2, planar, conjugated, cyclic. How do you use 4n plus 2? What does that mean?
Well, you count the pi electrons, so each double bond you count 2 pi electrons. And if it comes out to a positive integer, then it's aromatic.
Right, so you have to count your pi electrons, and you need to get a positive integer when you plug. Basically, if you put 0, 1, 2, 3, any positive integer into n, and you can get that number of pi electrons that you have, then that's aromatic. Or you can think about it, you can solve it, so you can set this equal to the number of pi electrons that you have, and if n comes out to an even integer, or it works as 0, then it's aromatic. So for letter I, how many pi electrons does it have? 6, right? 1, 2, 3, 4, 5, 6. So if you put n equals 1 in 4n plus 2, you would get 6. Or if you solve it for 4n plus 2 equals 6, you would get 1, n equals 1. So as long as n is an integer, or you can make n 0, then that number works. So that is aromatic. So number 1 works. And then what about number 2? How many pi electrons are in number 2? 14 pi electrons or 7 pi bonds, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 14. Let's just maybe solve it, because I don't know, I'm bad at math. N equals 3, right? So we got a integer, so that would be aromatic. Does that make sense? And it's planar, and it's conjugated as well, right? Okay, any questions on that one? Number 2? Or I mean, yeah, I guess that's 2. Okay, and then for the third one, how many pi electrons do we have? 6. Right, so that also works. And then the carbocations and the anions, they contribute to resonance, right? So we need those carbocations there in order to have resonance all around the ring. So without them, would it be aromatic? No, because it wouldn't be fully conjugated, is what I mean, if you didn't have the cations. So you need those. So the answer is A, it's all of them. Any questions on that? Can you guys do the same thing for hetero cyclic molecules. I didn't put any of them in there. But for something like that, how many would it have? 6, right? So why is that? Yeah, you just count one of the lone pairs from the oxygen. The way that I always think about it is like only one's going to fit when they have their actually electron clouds when you draw them in there. So you only count one of them. And then also, there's things like this. So, yes. So the carbocations are what make it conjugated. So because the carbocations are here, I can move this double bond over, and then that carbocation is going to move over here. And that's how we're going to be able to go all the way around the ring. Without the carbocations, there'd be these spaces, and so the conjugation wouldn't fully go around. Does that make sense? Okay. And then for something that looks more like this on the bottom, how many would this have? 6, right. So we count the 1 from the nitrogen, right, the 2 from these bonds, and then why don't we count this one? Yeah, the double bond's taking up the space. So if the heteroatom is directly on a double bond, then you don't count those lone pairs either. So this one would also be 6, just like that one. So you can get anything like that. They could be heteroatoms or not. It just depends. But you definitely get questions on determining aromaticity. Okay. So this is acids and bases. So for this question, it says, which structure helps explain why aniline ion is a stronger acid than an ammonium ion? So we're looking at these resonance structures. So what's one way to answer this question? How is orthopara? Not quite. You would. We're looking for more a resonance structure. It's almost like a orga 1 thing. That's true. There's something really kind of interesting about this question that you can use to just answer it right off the bat without even knowing what it's asking you, actually. Does anybody see it? What about the positive? It's not just the fact that the nitrogen has a positive, but does the nitrogen need to have a positive if it has 4 bonds? If a nitrogen has 4 bonds instead of 3, would it have a positive charge? Yes, right? So for letter D, when the nitrogen has 4 bonds and it doesn't have a positive charge, is that even drawn correctly? No, that's drawn incorrectly. What's wrong with A and C? Yeah, nitrogen has 5 bonds, so that's not even, there's only one actual correct structure. So you didn't even, if you notice that, you really wouldn't even have to think about the acid and basic part of it. So a lot of these questions, just pay attention to, sometimes I'll ask you which one of these is the most stable version of this, and only one of them is even that compound anyway. So pay attention to like things like that. Like if you don't know, just look at, oh, well, do these structures look correct? Or try and answer it based on as much as you can. And for these, only one of them was drawn correctly, so that's pretty awesome. Yes? Are the answers conjugate bases? No, they're just, yeah, actually, yeah. They're supposed to be conjugate bases. So this is a resonance structure of the conjugate base after it lost a hydrogen. And then these are all just incorrect resonance structures anyway. But yeah, this would be the conjugate base of aniline ion. Any other questions? Does that make sense? So just little things like that. Put 5 bonds on a nitrogen, and you might not notice. Okay. This one. What is the order of acid strength from strongest acid to weakest acid? So how would we answer this question? What was that?
Right amount and see which one has hydrogen at best.
Yeah, which one is going to be the best at donating the hydrogen? So how else could you think about that?
Well, when it donates that hydrogen, it'll have negative charge, and then you can say which one helps to stabilize it the most.
Yeah, so which one has the most stable conjugate base is the way that I like to think about it. There's a bunch of ways you can do these questions, but I usually just think of if each of these acids were to act as an acid and donate a proton, which one will have the most stable base? So which one's most likely to donate a proton because it's going to be more stable? So you can draw the bases of all of them. Oh. I protonated them. Okay. So which one of these bases is the strongest, or the most stable? I'm sorry. The third one, right? Why? Yeah, because the fluorines are not only the most electronegative atom, but it's also in the position 1 carbon closer than number 2, right? Or it's supposed to be. So all the fluorines are electronegative, so they have a dipole that's pulling electrons away from that negative charge, helping to stabilize it, right? So the fluorines are more electronegative, so this is more stable than the chlorines. And then this is one space off, so that one's going to be right after those. And then this one doesn't have anything helping to stabilize the negative charge, so its base is the least stable, so it's going to be the least acidic, right? So we should have 3 first, then 4, then 2, and then 1, so it's C. Any questions on that one? Okay. All right, so identify the weakest acid. So the last question was kind of orgo 1 based. This is more orgo 2 based, right? Why is this orgo 2 based? What is it asking about? What was it? It is. It's from the aromaticity chapter. What concepts from the aromaticity chapter? Yeah, activators and deactivators, or electron donating and electron withdrawing groups, right? It's actually the same exact kind of premise as this question, where we're saying that something that's withdrawing electrons is stabilizing the negative charge, right? In chapter 18, you learned about electron donating and withdrawing groups, so you can use the same thing. Something that's withdrawing electrons from a negative charge is going to stabilize it, right? And something that's donating electrons to a negative charge is going to destabilize it. So when you're looking at these acids, the different substituents can help you decide which one's going to be stronger based on which one's going to have a more stable conjugate base. So for the first one, you have nothing on the ring, so it's just a regular carboxylic acid. For the second one, you have an NO2. Is that a withdrawing group or a donating group? Withdrawing, yeah, and it's a strong withdrawing group. So we have this that would, if we deprotonated this and had a negative charge, you see how that would be withdrawing electrons from it, so it would help to stabilize our negative charge, right? So that's going to make this a strong or a weak acid? Strong, right? Because it's going to have a more stable conjugate base. It's going to be more likely to give up a proton because it's going to be more stable. So this is a strong acid, but we're looking for the weakest acid, right? So that's not it. What about C? What is this, an activator or a deactivator? Activator, yeah. Something that helps is if they have lone pairs directly on the first substituent, a lot of times that's an activator because the electrons will go into the ring. So if it's an activator, it's adding electrons to the ring. So what is that going to do to the base? Stabilize it or destabilize it? Destabilize it, right? Yeah, if you're adding electrons to a negative charge, it's going to destabilize it. So is that going to make the acid stronger or weaker? Weaker, right? Because it's going to have a less stable conjugate base. Does that make sense? So this one's a pretty weak acid. And then let's check this one. What is a Cl? Donating or withdrawing? Withdrawing. It's actually an electron withdrawing group, even though it's an orthopara director. So remember that. Chlorines are weak deactivators, so they are electron withdrawing, but they are orthopara directors. So this one's withdrawing, so that's going to make the acid stronger, right? And then this one has nothing happening to it, but this one is being destabilized as a conjugate base, so this one's going to be the weakest. Yes?
If you had 3 electron withdrawing groups, would A be the weakest acid? Like
Yeah. So if C, B, and D were all electron withdrawing groups, then yes, A would be the weakest acid because the other ones are going to be stronger because of that. Any other questions? That's a good one. What if it, instead of carboxylic acid, was something like this? And it was asking about this acting as a base. How would adding an electron, donating or withdrawing group, change the basicity of that? If I added something that was donating like this, would that make it a stronger or a weaker base? Stronger base, right? For the same reason, because when this acts as a base, so you get the conjugate acid, right? So if this pulled off a proton and became H3 and grabbed a positive charge, if something is donating electrons to that positive charge, it's going to make it more stable. So it's reverse for bases, and I've seen them ask questions of both. In fact, they have them like right next to each other in the study guide. So it can just as easily ask you which one of these is the strongest base or whatever on the same kind of topic. Does that make sense? Any questions? Okay. All right, so we're still on acids and bases. I remember seeing a lot of questions like this. That doesn't mean that you're going to get a lot of questions like this, but I remember seeing a lot of questions like this. Just kind of which one of these protons is more acidic, or rank these protons from more to least acidic. So what do you, I know the answer's on there, but what do you guys think? You would have said C? Yeah. Why would you think C over A? Do you guys remember this? You remember that from like Orca 1, ARIA? No. It's like atom resonance induction orbital. No. Okay. Well, you want to keep in mind the atom first, meaning what is the proton on, right? So A is on an oxygen, which is really electronegative, meaning that a negative charge is going to be on an oxygen, versus C is on a carbon. So a carbon is less electronegative than an oxygen. So you want to hold atom priority over resonance priority most of the time. There can be exceptions, but.
So if O is oxygen is more electronegative, why would it want to lose the proton?
It's more stable to have a negative charge on something that's more electronegative than something that's less electronegative. And then this also has resonance too, right? This can go all into the ring, the negative charge on the oxygen that you get after that acts as an acid. While this one has resonance with the oxygen, this has not only more resonance, but A also has a more electronegative atom. So that's why the answer is A. So keep that in mind. A lot of people will forget the atom and go straight to resonance. But
So between C and D, because they're both directly next to, oh no, would H be more because it's closer to that carbonyl oxygen?
that's a good question. I want to say that it's C, but I can't like explain to you why I think that it's C. I think it's. I don't think that you want a negative charge. It's called aryl, like right on a double bond, because it would be like right on the. I think that that's unstable. Yeah, C is alpha to it, which is much better. You still get the resonance, but it's not right on the negative charge. So I would say C. I would even think B is better than D, just because again, they really don't like having negative charges on double bonds. Okay, any other questions? That's a good, because C has resonance with the oxygen, but B can go all the way into the ring, which I want to say C because it's an alpha proton for sure. But if you remember, I've seen questions in the enolate chapter where you deprotonated something because it was next to a benzene ring as well. So that'd be pretty close to call, but I would think C. Okay. Any other questions? Yes.
So OH has more priority than NH that is an alpha, like greatness of priority?
Yeah, in this case, OH, it's not just a regular alcohol, it's an alcohol with resonance as well, which is also, because the alpha carbon has resonance with an oxygen, but this has resonance with the whole benzene ring and it's on an oxygen. So I would say if you just had a plain alcohol, that being the alpha proton would be more acidic than a plain alcohol. But because this is an alcohol right on a benzene ring, that's why it beats it in both like arenas, in A and R. Does that make sense? Okay, no problem. Any other questions? Okay. So stereoisomerism, this is my least favorite of all the topics. Okay, so which molecule has the R configuration? So how would you guys go about doing this? Yeah, I don't have a quick or cool way to do this. I would just start labeling priority groups basically. So for A, what would be priority group 1? The OH, right? Cool. And then what would be the next one? That, and then this would be 3, right? So the arrow's going that way, which is not clockwise, right? This is counterclockwise, so it's S. Clockwise is R, counterclockwise is S. Why does, okay, so again, it's kind of like Ario again, so we're going with atom first. So if you start with, you're starting from this carbon, this is an oxygen, and this first one is a carbon. So oxygen beats carbon because it's more electronegative. And then you'll go one space further. So if these were both carbons and this was just a carbon chain, then this would win because the second atom was an oxygen. But you do it one at a time. Okay. So that's S. And then you also want to keep in mind your lowest priority group, in this case, which is a hydrogen, needs to be on a dash, right? If your lowest priority group isn't on a dash, what are you supposed to do? Switch it. Yeah, so if our lowest priority group, if the H was on a wedge, then instead of S, it would be R. So keep that in mind, because they definitely do that. Things like Fisher projections, you always have to flip, right? I don't know if I have one on here. I can just do one really quick if I don't. I don't. Okay. So what about B? What's the first priority group? OH still, right? Because the oxygen versus carbons. And then what about these two? This one, right? Because this one has 2 oxygens. This one only has 1. Yeah. And then 4, right? So it's going this way, which is also counterclockwise. So S. Then if we're looking at C, it's going to be the same thing, right? This is also 1. This is also 2. This is also 3. But this way is going clockwise. So that would be R. And then just to check, this nitrile would be above this methyl, right? Because this triple bond and this nitrogen is way more electronegative than just a methyl. So this would go that way, which is also S. So the answer is C.
The hydrogen of the lowest priority to be on a dash or on a straight line?
A dash. You want it to be on a dash. You want it to be behind the paper, basically.
Does it matter for like C that our OH is on a wedge? Like isn't the highest priority supposed to be on a wedge as well?
I don't think, no, your highest priority group doesn't have to be on a wedge, right? Because our highest priority groups were all in the plane, right? OH was in the plane, OH was in the plane, OH wasn't on a wedge. You see that? Priority group 1 wasn't on a wedge. So your highest priority group doesn't have to be on a wedge, but your lowest priority group should be on a dash.
So if the lowest priority group is in the plane and like not on a wedge or dash, we would have to flip it.
I think if it's on Those are usually on there. So if you have something like this, this is just a methyl. So when you're on a Fischer projection, in what plane are your H's or your horizontal things on? Wedges. Yeah, your horizontals on a Fischer projection are on a wedge. So you have to keep that in mind because your lowest priority group, you make this a CH3. I guess it doesn't matter, but it does matter because then it wouldn't be a chiral center. So everything that's horizontal is on a wedge, right? So what does that mean if your H is on the wedge or on horizontal? You got to flip it, right? So for this one, what would be priority group number 1 for this carbon? The carboxylic acid group, right? Because we have a carbon here and a carbon here and a carbon here. But this carbon is directly bonded to a double bonded O, where this carbon is only directly bonded to a single bonded oxygen. So this one is higher. And then this would be 2. And then this would be 3. I'm sorry. That's what I meant. So it goes this way, right? So that's S, but really it's R, right? Because the hydrogen is on a wedge, so you have to flip it. Does that make sense?
So if you have a hydrogen on any horizontal line, you're going to need to flip it?
Yeah, exactly. Even if it's not a hydrogen, even if it's your lowest priority group, like just a methyl is your lowest priority group, if it's on the horizontal, then it's on a wedge, and then you have to flip it for Fischer projections.
So are there no dashes representative on the Fischer?
I don't know. I only know the wedges because it matters for configuration, honestly. I don't remember. That's what I thought, but I'm honestly, I don't know. All I know is that the horizontals are wedges, and so you've got to flip it, yes. For a Fischer projection? No, they don't tell you. Not for Fischer projections. I never see like an arrow on it or anything. Oh, I mean, they'll tell you if you're talking about the first one or the bottom one, which chiral center. Yeah, exactly. Yeah. Unless there's only one chiral center. I've seen that before. Like, they'll trick you by making this both hydrogens, right? So then you don't have 4 different priority groups. And then they're asking about the chiral center, and first you have to know which one is a chiral center, right? So for something to be a chiral center, you have to have 4 different priority groups. None of them can be the same. Okay. So this one, which isomer is most stable? How would you answer this question? Yeah, equatorial. So just pick the one that has all the bigger atoms, equatorial. So the way that I always did equatorial is if it's pointing with the chair, that's axial, and if it's at an angle against the chair, that's equatorial. It's not like a super scientific way, but it makes sense to me. So this one would be axial, right? The bigger group. And then this would be what? Equatorial, right? Because it's going against it at an angle. And then what about this one? Equatorial. Okay, so we have 2 equatorials and an axial. And then what is this? Equatorial, and this one. Equatorial, and this one. Right. Axial, equatorial, equatorial, axial, axial, equatorial. So B wins, right, because they're all equatorial. If they didn't give you, they could have given you where, 2 of them were equatorial at 2 positions and 1 axial at the other, right? If that makes sense. So you could have had no choices where they were all equatorial, and you would have to decide, say, between, A and C. How would you decide between those 2? Which one has the larger groups in equatorial? So which one would be more stable, A or C? C, yeah, between A or C, C would be more stable because you have the OH group and the larger carbon group in the equatorial position and the smaller group in the axial position, whereas in A you have the big OH group, the super electronegative OH group in the axial position. So C would be more stable. Any questions on that? Cool. Okay, 11. the product of this reaction will be what? So when you use HCl on a double bond, is that 1 or 2-step process? 2-step, right? So what does that mean that you have? A carbocation, right? So where is it going to go, the carbocation? In the more stable position, right? The tertiary side. So you'll have an intermediate like this. Right? Because your carbocation is going to go in the more stable position, and then that's where your chlorine is going to add. So you'll get this. So would we start assigning priority groups to this?
No.
Why not? Okay, so then what would that be? Race mate. In this case, though, there's something else to notice. There's not 4 different priority groups anyway. So it's true that because there's a carbocation, it will add from both sides. So you could get it adding in a wedge or a das position if it was chiral. But in this case, it's not, right? Because these 2 carbon groups are exactly the same. Does that make sense? So you don't have 4 different priority groups, and you need 4 different priority groups for it to be a chiral center. So it has to be achiral, so it's A. Any questions on that? Achiral means that it doesn't have an R and S, basically. Chiral is something you learned in Orgo 1 about being optically active and stuff like that. It's basically just, to be chiral, you have to be a carbon that has 4 different priority groups, so 4 different things attached to it. And then your chirality will either be R or S. But in this case, it's not a chiral center because 2 of the groups are the same. Any questions? Yes. Oh, that's a good question. That's an Orgo 1 thing. It's like they're mirror images and something else. I'm not very good at the meso compound stuff, to be honest. I think it's basically that they're the same compound, but they're like flipped. It has to do with symmetry. But yeah, I don't have a really good answer for you on that one. It's definitely fair game though on the ACS. So. We don't have any of those on my review though. So. Any other questions? Okay. Oh, this is a good one. So this one is just asking how many stereocenters, oh my goodness, how many stereocenters or chiral centers are present in this molecule? So that's what I was just talking about. So we have to pick the different chiral carbons, the different carbons that have 4 different priority groups. So what about, do you think, is this one a chiral center? Let's see. Well, this carbon's different because it's closer to the chlorine than this carbon, right? So these 2 are different. But what about these 2? Exactly the same, right? Those 2 methyls are exactly the same. So this carbon is not a chiral center. What about this carbon? Yeah, right? You have a chlorine. That would be your priority group number 1. Then you have this carbon over here with all these other carbons and an oxygen. That would probably be 2. This would be 3. And then you have a hydrogen here, right? So this is a chiral center. What about this carbon? Yeah, right? I would think this would be your highest priority group. And then this one over here. I'm sorry, this is getting hard to read, but you have 4 different groups, right? Because this carbon is in a different environment than this carbon. And this carbon's in a different environment, and then you also have an H there, which would be your lowest priority group. So that's another chiral center. And then, where's the other one? This one, right? So that one's kind of hard to see based on the way that they drew it. But this carbon is attached to the ring. It's attached directly to an oxygen. It's attached directly to a hydrogen, and then it's also attached to this carbon. So that actually does have 4 different priority groups. So you have 3 stereocenters. Because there's 2 hydrogens on it. Is this what you're talking about? So those are the same. Any other questions on this one?
To find this, like how many stereoisomers, we use that as like the 2 with the square, the n.
Oh, I don't know. That's a good question. Yeah, to find how many stereoisomers. There's definitely a formula for that because there's all the different combinations, but I don't know it. I don't know if you have to know that. I haven't seen that come up, but it definitely could. Was it on here? Yeah, then good point. I don't know that one. I think this question was, it's like an easy concept, but I think this one was kind of hard to find. So, I don't know, just look at them all pretty closely. Any other questions on this? Just so you guys know, she was asking about, there's like a formula where you can find out the different amount of stereoisomers based on the different stereocenters. And I don't know that formula, and I think there is a question in the ACS study guide about it, so you might want to look it up. Okay. It was what? 2 to the n. I'm sure that it's really easy math, but it makes no sense to me. Okay. Yeah, so I'm assuming n would be the number of chiral or stereocenters, and then that would equal your stereoisomers.
That's like the possible amount you can have, and the mesos you subtract.
Excellent point. So he was saying that also then the meso compounds could come into play. So if you have really good symmetry and 2 of your stereoisomers are actually the same compound, so they're meso compounds, then this would be your theoretical amount of stereoisomers, but you would have to subtract the amount of meso compounds. Does that make sense? So it's kind of getting at your question. You'd have to subtract the amount of stereoisomers that are basically the same due to symmetry. Okay. So which alkyl halide would you expect to undergo an SN1 hydrolysis most rapidly? So SN1, did we want, is that 2 steps or 1 step? 2 steps. So it does have the carbocation thing, right? Carbocation rearrangement. So it will go, we want, what do we want? What kind of alkyl halide do we want? Tertiary, right? Does that make sense? Because we get the carbocation, so it's 2 steps. So a tertiary carbocation is more stable. So if SN1 is 2 steps, we want a tertiary alkyl halide. You'll notice that these are all tertiary, so that doesn't help us. What else can we look at? What's the difference between these? Electronegativity. There's also another difference, atom size. Yeah. I don't know if you guys remember that, but what does atom size have to do with these kind of reactions? Yeah, the larger the atom, the more readily it wants to leave. So the bigger atoms make better leaving groups, basically. Since it's 2 steps, you have the first step, it just leaves, and the second step, you have the attack. So a lot of people are focused on the tertiary and primary part, but also there's the idea that the larger atoms are better leaving groups as well. So when comparing these, which one of these, I, Br, Cl, or F, fluorine, is the biggest atom? I. I is the biggest atom, so I is the best leaving group. So that's why A will happen the most rapidly. Does that make sense?
So you said the large atom.
Leave the easiest. The larger the atom, the easier they leave. Any questions on that one?
Are halogens the best leaving groups, like overall, like considering everything else?
I mean, that works a lot of the times. I'm sure that there are instances where it's not always true. But we do use halogens as leaving groups. For instance, like water is a really good leaving group. So I don't know that they're always the best, but if you see a halogen, we do use them as leaving groups a lot. So they are very good, but I don't know if they're always the best. Okay, what's the major product of this reaction shown? So what's happening here? Do you guys remember this kind of a reaction? Elimination? Yeah. Is our base a bulky base or not a bulky base? Not a bulky. So are we going to get the more substituted or the least substituted double bond? More substituted, right? So that's from Orgo 1. When you do these eliminations of your alkyl halide or whatever it is, the bulky base is going to give you the least stable, whereas the non-bulky base is going to give you the more stable, the more substituted. The bulky base example would be like tert butoxide. I don't really know another one. But yeah, tert butoxide is the most common. So anyway, we have the non-bulky base, so we're going to go with the more substituted. So it can't be A because that's the least substituted. This one is one space away. It's not attached to where the bromine was, so we can cross that out immediately, right? Does that make sense? Okay. And then between C and B, how would you figure out which is the answer? Yeah, B is conjugated, so B is more stable. So while they're both the more substituted options, and typically you would get a mixture, and you will get a mixture, but it's asking for the major product, and the major product is going to be B because it's resonance stabilized. So you're going to get more of that product than the C product. A is least substituted, right? Because if you're trying to eliminate this on either this side, or this side, this carbon only has 2 hydrogens. It doesn't have any substituents, whereas these 2 carbons are connected to other carbons. Does that make sense?
So,
yes.
like, if you were like just looking at it, how would you tell that NaOCH is a base when you're doing like elimination?
It's this. Yeah, I mean, you can think of it. Yeah, and you can think of Na always leaves, right, and becomes Na plus. We're used to that. So if Na leaves and becomes Na plus, you would have OCH3 negative, which is a really basic, something like this. Really wants hydrogens, right? That's not very stable. So you can conceptually kind of realize that it's a strong base, but kind of memorizing that it does elimination, you kind of just have to memorize. But it's Naomi is how I always think about it, or just this one. But we've seen this a lot, or like NaOET, right? Those bases will do this elimination like Orgo 1, and they also do the enolate stuff that we did towards the end of Orgo 2, like alpha deprotonation. CH3OH does it too. Oh, in this reagent? No, it's just a solvent. Okay, predict the major product. This is kind of like the other ones. So how is this is this 1-step or 2-step? 2-step. So we have a carbocation rearrangement, so it's going to go to the more substituted carbon, right? So our Cl is going to add to the more substituted carbon. So it has to be D. Does that make sense? This one we have the carbon over here. The chlorine, and the chlorine is over here for this one. This one, I don't know what's going on. It doesn't add to the double bond. And this is the only one where the chlorine adds directly to the more substituted side of the double bond. Does that make sense? Okay. So predict the major product of the reaction shown. So what does B2H6 H2O2 NaOH do? Add water, anti-Markovnikov, or less substituted. Yes. Love this reagent. You're not done with it yet. It will probably come up on the ACS. It's came up a lot all semester. You learned it in Orgo 1, and you use it a lot in Orgo 2, so it'll probably come up on your ACS. This reagent adds water, anti-Markovnikov, or to the least substituted position. So if we're looking at the double bond, the least substituted position would be right here. So this has an OH there. This one added an OH to the more substituted position. This one is also at the least substituted, and then this one added 2 OHs, which this reagent does not do. There is a reagent that you learned in Orgo 1 that adds OHs to both sides of a double bond. I don't remember what it is, but there is a reagent that does that. It's like, no, I don't remember. I'm not even going to try to guess. I don't know. I haven't really seen it come up, but if you remember, you learned one that does anti-OHs and one that does syn-OHs across the double bond. Yeah, I don't know. You did it in Orgo 1. You might want to look it up, but it's not this reagent. This one, definitely no. It adds water. Anti-Markovnikov. So how do we know the difference between these two? Oh, yeah, that's true. Trans is more stable. But there's also, if you remember, when you went over these addition reagents, they specify which one adds syn and which ones add anti, basically. So some of them will add in the least stable conformation anyway, but this one in particular adds anti. So it's kind of like a memory question, but if you did answer it based off of A being more stable, you'd be correct in this case, but you wouldn't always be correct. So when you learned these reagents in Orgo 1, they have different, some of them add across the double bond syn and some of them add across the double bond anti. Anti is more common because it's more stable, but some of them do add syn, meaning they do add them on the both on the same side. But this reagent adds them anti. Okay. If you had to guess, I would guess anti, but oh yes. Yeah, this is the same as BH3-THF. So you'll notice some of the reagents are written a little bit differently sometimes because it's a nationwide exam and reagents can be, slightly different. Also, sometimes you'll see things written out that you only knew acronyms for. So like when I was taking the exam, I remember I saw Lindlar's, like the actual drawing of Lindlar's catalyst, and I only know it as Lindlar's catalyst. So I was like, I didn't know what it was. Or MCPBA, I've seen that one before, like drawn out, and I didn't know what it was. So I don't know. That's why I recommend going through the ACS study guide because maybe some of them will pop up. But that's happened to me before, so just a warning. Okay. With which reagents can the ketone shown be prepared via a Diels-Alder reaction? So we did Diels-Alder this semester. This isn't big enough. Oh well. We did Diels-Alder this semester, and we're trying to make this guy. So how would you guys go about answering this question? What do you need to do a Diels-Alder reaction? Yeah, you need a diene and a dienophile. So that's something we can use. Are either of these a diene? No, right? What about here? Yeah, this is a diene and this is my dienophile, right? So that can at least do with Diels-Alder. What about here? No. So I'm not saying that you can't do cycloadditions with these. You can do a 2-pi cycloaddition. I think you need HV. But it's not a Diels-Alder, right? Because a Diels-Alder is a diene and a dienophile, right? It was 4-pi plus 2-pi is Diels-Alder, right? So this would be like a 4-pi and this would be like a 2-pi. Because we also have a diene and a dienophile here. So both of these can do Diels-Alder. Now we just have to pick the one that's going to give us this reagent. I'm sorry, this product. So something you could do would be, if you honestly had no idea, you could count carbons. And you could get your answer that way, and you would find that this one has extra carbons. If you add these two together, you'll get more carbons than you have here. So something that simple can get you the answer on a question, so keep that in mind. But you could also just realize, I'm going to redraw it. If you know the mechanism, this will add like this. And that's going to give you the benzene ring with the double bond on the far side like you need. And that, this diene comes from D. But again, you could have just counted the carbons and noticed that you had 2 extra carbons right here. That would come up as a bridge when you were making your product, but we didn't have any kind of weird bridge thing, so we were good. Any questions?
All
Yeah, that's true. Even if you didn't know what a diene or a dienophile was, you could have said, all right, well, if I add these together, I'm going to have this many carbons. If I add these together, and realize that you would never get the correct amount of carbons unless you pick D. So that's a really easy way to answer this question. And some of the questions are like that, which is awesome. So keep that in mind. Definitely keep in mind counting your carbons, or are these resonance structures even correct? Because a lot of times you can get your answer that way. So don't give up on a question even if you don't know what it's asking. Definitely count your carbons first, because sometimes that works. Or it can at least cross off like half the answer choices. Okay, what is the major product of the reaction shown? So I picked this one because I never remember doing anything quite like this exact reaction when I took Orgo 2, but I ended up getting the problem right when I went through the study guide, because I know how the things react, because you did learn kind of how these different atoms will react with each other. So if you think about that, if you think about how a primary amine reacts with a ketone, what do you get? An imine, right? Do you guys remember that? Primary amines react with ketones or aldehydes to give you imines. Secondary amines react with ketones or aldehydes to give you N-amines. So using that, this is a primary amine, but its R group just has some nitrogens and ketones on it. It's not just a regular R group, right? So if we answer the question based on that, then you would get B as the answer, because this would be the imine that would come from adding these two together. Because an imine is just when the nitrogen replaces the oxygen on the carbonyl, and you keep the double bonds in the exact same position. So you basically can just rewrite this oxygen with the nitrogen, the primary amine nitrogen, and then the R group would just be everything that's attached to it. So that's going to be B. A adds an extra nitrogen somehow. There's 3. Oh, no, it switches it.
Yeah, I think you said, we had that question on one of our exams, and you said that you couldn't use the one on the right because it's not like making hydrogen. It's like connected to just a double bond.
The hydrogen's connected to?
The amine.
Yeah, you don't want to use that side. That's just a rule, basically. I didn't even realize they had that answer. This one, they lose a nitrogen somehow, and this one, they added it to the one in the middle, which would be a secondary nitrogen, so then it would make some kind of an N-amine, so that doesn't make sense. Imine. Ketone or aldehyde plus primary amine equals imine. And then ketone or aldehyde plus secondary amine equals N-amine. That's why you can't do D, right? Because this would be secondaries. And I don't know where this oxygen comes from. This one's just all wrong. Oh, I see what they did. That's still not right. Okay. Okay, 17. Which reagent will accomplish the conversion shown? So what are we doing here? Yeah, we're adding to the beta carbon. What else is it called? 1,4 addition. So whatever way you want to think about it. So you kind of learned this at 2 separate points in your class, which is weird. You learned it in the very beginning when you did 1,2 versus 1,4 addition, so when you were comparing Gilman's versus Grignard's. And then you actually learned it again when you did Michael addition, because Gilman's is actually a Michael donor. So that's why it adds to the beta carbon, just like your Michael donors do. Does that make sense? So the chart in the Klein book has Gilman's with a bunch of other Michael donors, and you can see that, oh, wow, this is a Michael donor. So you learned this twice. So that being said, what's going to be your answer? Gilman's, right, D. The one with the, Gilman's always has a copper. So that's the way you can spot Gilman's. It'll be whatever kind of carbon group you're adding, you have it twice, even though you only add it once. And then it'll be right next to a copper lithium. So that'll be your Gilman's reagent. And again, that adds 1,4. Yeah, perfect. Any questions on that one? You can't use Grignard's because it will add 1,2. So Grignard's would have added 1,2. It would have added to the carbonyl carbon, right? And you would have got, what would have happened to your carbonyl oxygen? it would turn into an alcohol, right? Because you have an addition, not a substitution. Just keep that in mind. A lot of people start thinking Grignard's always goes twice, but not if you have an addition, right? Grignard's goes twice if you have a substitution. If you have an addition, it can't go twice because you don't get the reestablishment of the carbonyl. If you guys remember that. Okay. And CHLI, this would also be considered a Grignard's. Okay, what time is it? Cool. Okay. Which set of ketone and aldehyde will provide the same alcohol product when submitted to the reaction conditions shown? I keep putting this at really crooked angle. So we're matching up like 1 with the reagents of 1 and then 2 with the reagents of 2 to get this same product. So this is an example. Sometimes they're kind of confusing, like just how they have them set up. So this one takes a couple seconds to like figure it out. But we're taking these different reagents and matching up the 1 up with 1 and 2 with 2 to try and get the same product for both. So what does LaH-H2O do? Reduces, yeah, it's a reduction. So all of these ketones, basically it's just going to turn them into alcohols right where they are. So wherever your ketone is, that's going to become an alcohol right there. So I think that's a really easy way to mark off some answers. So we need a number 1 reagent that's exactly like the number 3, except it has a carbonyl right where the oxygen is. Because that carbonyl is going to get reduced by the LAH to become the alcohol. So which one of these has a reagent in number 1 that's exactly like 3 with a carbonyl? B, yeah, B, and what else? And D. So we can cross out A and C, right? Because A and C, these are both going to become alcohols, but they're not going to look anything like this, because the carbon structure isn't going to change. So between B and D, number 1 will both work, so now we need to find out about number 2. So yeah, count the carbons. If you were completely lost on this, you could just count the carbons, and that will give you your answer. So that's working for us again. So if we wanted to do that, we need 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 carbons in our product. We're adding 1, 2, 3, 4, 5, 6. So this needs to have 4. 1, 2, 3, 4. 1, 2, 3, 4, 5, 6, 7. Right? So this one, you would get too many carbons. Do you guys see how I did that? So if you see how it works, if you remember using Grignard's on an aldehyde or ketone, which you should, because you're definitely going to get a lot of questions like that as well, that's really helpful, and you can imagine how they add together. But if you happen to forget, or if you're just trying to be quick, counting carbons is actually a pretty quick, effective way to answer this question. But you do need to know how Grignard's works with carbonyls and stuff. So you need to be able to visualize this attacking right here and the oxygen coming up and getting protonated and becoming the alcohol. It does not. So he asks, does lithium, aluminum, hydride not reduce the double bond? And it doesn't. What's the one that reduces the double bond? H2PDC, yeah. So H2PDC can reduce both, but it prioritizes double bonds. But it can reduce both carbonyls and double bonds. Lithium, aluminum, hydride, only carbonyls. Okay.
So when you have these 2 PDC, like if they give you access, would it reduce everything?
Yeah, so if they give you enough moles of H2PDC, it should reduce everything. If they only give you like half, basically, and you have 1 carbonyl and 1 double bond, pick the double bond. I would know for sure that H2PDC reduces both, and LAH doesn't. Yeah, it won't touch the double bond. Okay. Nucleophilic and electrophilic aromatic reactions. So we're moving on to the aromatic chapter. I love this chapter. So which structure represents a major intermediate of the bromination of nitrobenzene? So we are starting with nitrobenzene, right? And we're brominating it You won't have to do all of this to answer the problem, but just for a refresher, what's the reagent to do bromination? Yeah, Br2, Fe, Br3, right, with the catalyst. And then NO2 we said was what, activator or deactivator? Deactivator, so it's what kind of directing? Meta, right? So this is a deactivator. It's meta directing. So, and again, this is ortho-para, this is meta. I'm sorry, this is ortho, this is meta, and this is para. So NO2 is a meta director, so we're going to get additions of Br at either this or this position. So it's asking for the intermediate in this mechanism. So you don't get a lot of mechanism questions because it's multiple choice, but a lot of times they'll ask you intermediates, which sometimes, a lot of times, make you have to prove that you understand the mechanism. So what's the first thing we can look at and cross answers off? C and D, why? Yeah, because they're para. So we know that this is going to have to add in the meta position when we do the mechanism. And then what's the other thing we can use to decipher between A and B? So they were both aromatic to start with. So they were both these rings to start with. And now they're asking which of these intermediates is correct. So how can you determine? Yeah, well, you're doing addition. Which kind of addition? Electrophilic. So since this is an electrophilic addition, I'm sorry, in the mechanism, what's your electrophile? What does the double bond? So your double bond, remember, does the attacking of the Br2. So then you end up getting a positive charge. What's the one where you get the negative charge in resonance? Nucleophilic, right? Because then you have the nucleophile as your reagent, and your nucleophile attacks your benzene ring, adding electrons to your benzene ring, which is why in nucleophilic you would get a negative charge resonance. But when we're doing an electrophilic reaction like bromination, you get the positive charge in your resonance structure. So that's why it's A versus B. Does that make sense? Yes. How do I know it's a meta director? You kind of have to, all deactivators are meta directors, but you kind of have to memorize which ones are deactivators. It's not necessarily a rule and it doesn't always work, but if you don't have them all memorized or you forget, something I like to do is if you have lone pairs directly attached to the benzene ring, that's an activator, right? Because the lone pairs typically go in and contribute to resonance, so they're donating electrons. Versus if you have something like NO2 that has double bonds directly attached to the first atom in the substituent, that's usually a deactivator. Yeah, so just, it's not a rule and doesn't always work, but something that I use if you forget what's an activator or a deactivator is if you have lone pairs directly attached to the atom that's in the benzylic position, so right on the benzene ring, if you have lone pairs there, that's usually an activator. And then if you have this double bond, this isn't here. If you have this double bond right on the benzylic atom, then that's usually a deactivator. Yes?
I heard too that, like, you know, if it had multiple atoms, like NO2, I heard that if the second one is more like a negative, then the activator.
That's usually true. I can see that as well. If the second atom from the benzene position is more electronegative than the first, it's typically a deactivator. The pattern that I mostly see is the lone pairs versus the double bonds. So even something like this, right, that's a deactivator because you have the double bond right on that carbon, not the lone pairs. So that's what I use, but I also have them memorized. So, yeah, you know, it's up to you. Okay. This one. arrange in order of decreasing reactivity, fastest to slowest, towards HNO3, H2SO4. What is HNO3, H2SO4? What does that do? Nitration. We don't really need to know for this question, but actually you kind of have to know. So nitration is electrophilic or nucleophilic? Electrophilic. So if it's electrophilic, if you're donating electrons to the ring, is that good or bad for the reaction? Good. It's good for the reaction. If in an electrophilic reaction, the double bond on your ring is your electrophile, right? It does the attacking. I'm sorry, it's your nucleophile. Yeah, but when you do an electrophilic reaction, your double bond is what does the attacking from your ring. So if you're adding electrons to that double bond, that's going to make it more reactive, right? So your activators in this case are your electron donators, which makes sense because they're called activators. But when you're doing nucleophilic addition, it's the opposite, right? Because you're doing nucleophilic addition, you're getting attacked by a nucleophile, so you don't want to have more electrons added to your ring. You want to have electrons withdrawn from your ring when you're doing nucleophilic addition. Does that make sense? But nitration is electrophilic, so we're looking for the atom or the benzene ring that basically just has the strongest activator, is donating the most electrons. So this has nothing, right? What is this, an activator or a deactivator? A deactivator. It is orthopara directing, but it's a deactivator, so it's going to make it go slower. What is this? Deactivator. Is it stronger than BR? Yeah, it's even stronger. So this one is a weak deactivator. This is a moderate deactivator, I think. It might be strong. I don't remember, but it's better than BR.
BR have the lone pairs though?
Yeah, so that breaks the rules. So that's why I said it doesn't always work. Definitely doesn't always work, and that's a good point. The halides are deactivators because they're so electronegative. So they kind of have an exception. And then what about this one? Activator. And that one doesn't have lone pairs. So again, our groups are activators and they have lone pairs. But it does work sometimes sometimes it can help. So this is an activator. So which one is going to be the fastest? The one with the activator, right? So then we can cross out A and B because only C and D have that one the fastest, and then 1, right? Because that's the one that's not being deactivated. The ones that are being deactivated are going to go slower. So then you get your answer already. But then between 2 and 3, which one would be slower? Slower is 3, right? Because 3 is the one that's being the most deactivated. So that one's going to go the slowest. And again, that's for electrophilic. Electrophilic, your deactivators actually do deactivate the reaction. They make them go slower. It's the opposite for nucleophilic. So what I was trying to say, how you relate reactivity, so speed of reactivity, to whether something has an activator or a deactivator, is because if you're doing an electrophilic reaction, which we are, right? This is nitration is electrophilic, then your ring double bond is what's doing the attacking, right? Those electrons are what's doing the attacking. So if you have a donator or an activator, right? Those are donating electrons into the ring. That's going to make your double bond even more negative to do the attacking. Does that make sense? If you have something that's withdrawing electrons from your ring, it's not going to be as strong. Does that make sense? Yes.
So if you have like a deactivator interact faster with activators, the deactivators would it be the same inversely, like if you had a deactivated ring, activated would react faster with that?
Are you talking, would the opposite be for nucleophilic?
Yeah.
Yes, but there's also that, remember there's that orthopara and you need a substitute. Nucleophilic reactions have their own set of things that they need, but yes, in essence, the more deactivated the ring, the faster a nucleophilic aromatic substitution will be.
Okay.
But for electrophilic substitution, the more activated the ring, the faster.
Okay.
Is that making sense? I'm saying a lot without writing it, so I hope that you guys are getting it. Okay. Okay. What would the major product of this reaction be? So what is this? Alkylation, Friedel-Crafts. I know that you use it. This is Friedel-Crafts' alkylation. This is not acylation, right? This is alkylation. What's the difference? It's double bond O, right? If this was acylation, if we were to do the same thing with the acylation version, we would need this, right? That would be acylation. This is alkylation. Besides the fact that you get a double bonded O initially when you do the addition, what's the big difference between alkylation and acylation? Carbocation rearrangement, right? Acylation, you get no rearrangement. I don't know how to spell things, so. And then alkylation, you do get a rearrangement. So for alkylation, if you can have a rearrangement, you will get one. For acylation, if you don't have a rearrangement, I'm sorry, you cannot have a rearrangement. It also is with a catalyst, by the way. And then again, also you can reduce this. So with zinc and HCl, you can get rid of the carbonyl. You guys remember that? But the big difference is this one will rearrange and this one won't. So when it's asking for the major product of this alkylation question, we need to keep in mind that it will rearrange, right? Because when I write this out, as a carbocation, it would be primary, right? Because the Cl is attached right here. So since we would get a primary carbocation, it's going to rearrange to become secondary before we get the addition. So then what would be the answer? B, right? B is showing the rearrangement to the secondary position. A would be the trick answer, right? Because it looks like it's right. If you forgot that alkylation rearranges, though, you might pick A, but that would be incorrect. I don't know what's happening with C or D. They're adding it a bunch of weird ways. You can't change the carbon structure to make the carbocation tertiary like they're doing in C, but you can have a rearrangement from primary to secondary or secondary to tertiary if they're right, the positions are right next to each other like this. Does that make sense? Okay, so remember that. Remember alkylation will rearrange. You'll probably get a question on it. It was like a big theme in the aromatic section. And remember, acylation doesn't rearrange, for synthesis especially. And remember that you can reduce this to get rid of the carbonyl. Yeah, it's like the reduction is with zinc and HCl, I believe. Okay, cool. So this question is, which aryl chloride reacts the fastest with NaOH? So what kind of reaction is this? Nucleophilic. So NaOH is a strong nucleophile, right? You're going to get OH negative. So this is nucleophilic aromatic substitution. So it's asking which one reacts the fastest in nucleophilic aromatic substitution. So if I'm adding electrons to my ring, these extra electrons are going to attack my ring. What's going to make it happen faster? Deactivation, withdrawing electrons, or more positivity adding to the ring, right? Because I'm adding electrons to the ring. So for nucleophilic substitution, more electronegative or more withdrawing groups or more deactivators are going to make it happen faster. So this one doesn't have any deactivators, right? So that's not going to work. What about C? C has one, but B and D have two, right? So those are faster. And then what's the difference between B and D? Okay, so it does have to do with the fact that it's orthopara. But why does it have to do with the fact that it's orthopara?
The withdrawn group is closer to the Cl.
It's not because the withdrawing group is closer to the Cl.
Deactivating, shouldn't it be meta? So one should be meta.
That would be, so if a ring is already deactivated and you're adding something to it via electrophilic substitution, that's true, the addition will be meta. But when you're doing nucleophilic substitution, you don't have, what it does is it substitutes out for your Cl. So this is going to come in and substitute out for your leaving group in this reaction. So it's not going to add ortho, meta, or para, but the fact that the electron withdrawing groups are ortho para is better than meta. Does anybody know why? It has to do with your intermediates. Exactly, yeah, it has to do with the negative charge. If you're in Fraser's class, you guys remember you had to draw out all of the negative charges going around and showing why, which one is more stable and why it is ortho and para. So same thing for nucleophilic substitution. You'll get an intermediate where you have a negative charge right next to your withdrawing group for ortho and para. And if you do it, I'm not going to draw it all out because it'll take forever, but if you draw it all out, when you do meta, you won't get that negative charge right next to your withdrawing group when they're in the meta position to the chlorine. So once this ends up doing its substitution and everything, that's fine. But the fact that these are ortho-para, your deactivators are ortho-para to your leaving group, makes your nucleophilic substitution happen quicker because you get the intermediate where your negative charge is directly next to your electron withdrawing group. I would try to understand this concept because I could see it coming up as a question like, why is this more, like which one of these resonance structures is more stable and something like that. But you could also just memorize for nucleophilic aromatic substitution, it's better to have your electron withdrawing groups ortho and para to your leaving group than meta. Any questions on that? Okay, and that's for nucleophilic. So remember, they're opposites and just different in general. But okay, which sequence of reactions is expected to give the best yield of 3-nitrobenzoic acid? So we're trying to make this 3-nitrobenzoic acid. And these are our different mechanisms. Okay, so let's look at A. Do you guys like A? Why not? Because why? So what is a NO2 a electron withdrawing group or donating group? So it would add meta, right? But what's wrong with it? You can't do Friedel-Crafts on a strong, moderate to strong deactivated ring. You guys remember that? Yeah, that's back, okay? So no Friedel-Crafts, whether it's alkylation or acylation, on a moderately to strong deactivated ring. So you can do it on a weakly deactivated ring, so you can do it on a ring that has a halide on it. You can do Friedel-Crafts on a ring with a halide, but you can't do it on all the other deactivators. So no NO2s or double bonded groups or anything like that. Yeah, and then there was that little thing about you can't do it with something that has NH3 on the ring because it has some kind of reaction. I haven't seen that come up as much, but this definitely. But that's true. So except X for halide. If you have BR or whatever, you can do it. Okay, so that's why we can't do A, right? Because this is Friedel-Crafts and this ring is deactivated. Even though this would go in the meta position, and then once you add the CH3, what does this do, sodium chromate? Yeah, it oxidizes. It's an oxidizing reagent. What did you guys learn it as? Yeah, but there's a reagent that you guys learned that turns your methyl groups into carboxylic acids. Your KMNO4. You guys remember that? KMNO4 turns your benzylic carbons into carboxylic acids. That's what they're using. This is KMNO4. For A?
Cross out C.
Oh, for C.
And do that with Opera.
Yeah, yeah. So you can't do C because since we have a methyl already attached to our benzene ring, that's an activator. So when we go to add our nitrogen group, it's going to be orthopara, and our nitrogen group is meta to our carboxylic acid. Does that make sense? So that's out. And then A was out because this was deactivated, so we couldn't do Friedel-Crafts. And then B, we're going to turn our methyl, thank you, into a carboxylic acid with this first reagent. And then once it's a carboxylic acid, is this an activator or a deactivator? Deactivator. So, because it has the double bond right here, right? That's a deactivator. So is that meta or orthopara directed? Meta, which is what we want, right? These are meta. So then when you add your nitrogen, it's going to go to the meta position. What's wrong with D? Yeah, the reagent's wrong. It's not the, so you do have to, for this question, you did have to know the reagent for doing nitration, which is HNO3, H2SO4. And then you also had to understand no alkylation on a deactivated ring and orthopara directors and all of that. Any questions on this? Make sense? Okay. I remember a good amount of this stuff on the ACS, which I think is good. Okay, spectroscopy. Everybody hates spectroscopy, but I love spectroscopy. So, yay. It's okay. I don't like stereoisomerism, and some people think it's easy, so there's differences. Okay. Yeah, that's true. So he just said, I just want to cross everything out after 1500. You could, right? This is the fingerprint region, if you guys remember that. So anything from 1500 and below is called the fingerprint region, and it's useless to you. So you can just not pay attention to that. So step one, ignore that. Okay, something else I want to point out. What you should definitely do before you take the ACS. Does everybody have the ACS study guide? I would get the ACS study guide. If you're going to study more. I mean, isn't it tomorrow? So some people it's tomorrow, some people it's not. Okay, if you wanted to study more, I recommend the ACS study guide. Even if you're not going to, though, what you should really do is in the beginning of the spectroscopy section, borrow somebody else's study guide. They have a little chart of all the different numbers you need to know for IR and for H-NMR. And you should learn those because if you just Google it, there's like a billion numbers, right? Don't waste your time learning all of the different signals when you only have to know 8, right? So I recommend going on the ACS study guide, going to the spectroscopy section. It's in the beginning of the spectroscopy section. There's a little chart for the H-NMR numbers, the C-NMR numbers, and the IR numbers. Yeah, those two charts. Yes? Yeah, there's like a whole practice book. It's like $20. Okay. Yeah. But that has the chart. Okay. Yeah, definitely look at that. Even if it's like right before the exam, so you just have the numbers in your head, because it will help. Okay, so one of the numbers on the chart is for triple bonds. What number is for IR wave? What's the wave number for triple bonds on an IR graph, IR spectrum? 2100 nanometers. Something like that is carbon-carbon triple bond. And that's on the graph, again. Really hyping up the graph, but I think it's good. Okay. So this is showing up kind of blurred. Oh, that's pretty good. Okay, so do we have a peak in the 2100-ish region? Yeah, I would say so. So we probably have a triple bond. Do we all agree? Is there one answer choice that doesn't have a triple bond? D. Bam. Okay, one down. What's wrong with B? Why can't it be B? Yeah, so if there was an alcohol, there should be this broad OH peak over here, right? But we don't have that, so it can't be B. So a lot of times you're going to use what I don't have just as much as you're going to use what you do have on your IR graph. So it's just about functional groups. Okay, and then what's the difference between A and C? That's true, ester, but there's another difference. Yeah, exactly. There's an SP hybridized CH bond. And that is one of the ones on the chart, which is, again, why I recommend the chart, because it doesn't seem that important, but if you just know the chart, then you know it. So sp hybridized CH bonds have peaks around, 33,000? 31,000? 31,000. I don't know, over 3,000, yes.
How is that CH2 has like four of them connected to a carbon?
It's, they're just connected to each other.
Oh.
Did that help? Thank you.
It's 3,300.
It's 3,300? 3,100 is sp2. Okay. So sp hybridized CH bond should have a peak around 33,000. That's because, do you guys see these peaks right here? Right before 3,000? What are those? What are those indicating? sp3 CH bonds, right? You almost always have sp3 CH bonds. They're everywhere, all over the place, right? So you're always going to get this kind of like lump of signals right before 3,000. But when you have sp2 hybridized CH bonds or sp3 hybridized CH bonds, you should get a peak that's right above 3,000. Does that make sense? So since we don't have a peak above 3,000, right, the peak stops at 3,000, it can't be C because C has an sp hybridized CH bond. Does that make sense? So definitely recommend the chart. If you know the chart pretty well, you can answer almost all the spectroscopy questions. Is it what?
I said, do you have any tricks to memorize?
I do not have any tricks for memorizing the chart. I've just done this for 3 semesters, so I know the chart. But I would just look it over right before so you can recite it, however long you think it will take you to memorize them. I personally didn't memorize this carbon NMR numbers because I just know that carbon NMR is proportional to H-NMR, and that kind of helped me. But do whatever you think.
Did you say the ACS study guide has like level of difficulty questions kind of equivalent to the actual ACS?
Yeah, if you were to do the whole thing, which is huge, I would say that it's pretty similar. There are some really easy gimme questions, and then there's some that are pretty hard.
Yeah.
I think these are pretty good. I mean, these are the ones I picked. I also picked these because I'm good at explaining them. So there might be a little bit bias. But if you were to randomly pick like 5 questions from each section, I feel like that would be a pretty good, for me at least, it seemed like a pretty good estimation of the actual ACS.
Okay.
But I've heard people that disagree with me.
Okay.
But in my opinion, I would say they are actually pretty similar. I didn't see any questions that were the same, but I also had friends that said, oh, I did the whole study guide and some of those questions were exactly the same.
Yeah.
And I was like, I didn't notice that, but they could. I don't know. I thought it was pretty representative, but we'll see. You guys can tell me how it turns out. Okay. So which H-NMR spectrum is consistent with that of ethyl methyl sulfide? Okay. So this happened last time. I'm going to rewrite the H's because they're too tiny to see. So this is 3H, 3H, and 2H. This is 3H, 3H, and 2H, 2H, 3H. What is this? What is that one? Can you guys, is that 2H? Because anybody who has it on their laptop? I think it's 2H. Me too. 3H, and this one is 3H? Okay, I'm not gonna lie, that happened to me on the exam. Some things I was like having a hard time seeing, so if you wear reading glasses, bring them. It's like a small tip, but I don't know, maybe I can't see, but I had a problem with that. Okay, so what are these H values anyway? What are those? Yeah, something that starts with an I. They're integration values. Who remembers that from Orgal 1? Integration values? Yes. What do they mean?
How many hydrogens from the actual carbon that are?
Yeah, not the n+1 thing. It's the other thing. Okay, integration values, I'm going to write it. So integration values There are these H values that are on top of your signals, are the number of hydrogens giving rise to a signal. How is that different from multiplicity? Yeah, multiplicity is the number of hydrogens on the adjacent carbon. Multiplicity is basically this signal is a singlet, right? This signal is a triplet, and this signal is a quartet. That's explaining the number of hydrogens on the neighboring carbon, where these numbers on top, your integration values, are the number of hydrogens on that carbon giving rise to the signal. Does that make sense? We'll go over it a little bit more. So number of hydrogens on neighboring carbons. Okay, so let's use that to answer this question. Okay, so quick NMR review. If I'm looking at, first of all, how many different signals is this going to give me? Because that you really should know. 3, yeah. And I'm saying you should really know that because sometimes they'll straight up ask you a question, how many H-NMR signals does this molecule have? And they should be really easy questions. So definitely practice that. Go through the ACS study guide. You'll find them. There's a bunch. They do it for H-NMR and C-NMR. All you have to do is find which groups of hydrogens are in different electronic or chemical environments, basically. So this group of hydrogens, this group of hydrogens, and this group of hydrogens are all in different environments. They're not the same. This one's closer to the S than this one. This one has a carbon next to it. This one doesn't, right? So they're just a little bit different. So you have 3 different signals, okay? If we're looking at this signal, is it going to come up as a singlet, multiplet, triplet, or quartet? Triplet, why? Yeah, so then multiplicity has to do with the neighboring carbons, and the neighboring carbon has 2 hydrogens. So when you're looking at multiplicity, it's N plus 1. So we have 2 hydrogens plus 1, so it would be 3. So this would be a triplet, right? So that's going to be a triplet, but what's its integration value? Also 3, because it's 3 hydrogens that are giving rise to the signal. So it also has an integration value of 3. Does that make sense? Okay, move on to this one. So what is going to be this one's multiplicity? Quartet, right? You don't ever go through heteroatoms, so the neighboring carbon is a sulfide over here, so irrelevant. And then we move over here. This neighboring carbon has how many hydrogens? 3, right? So the neighboring carbon has 3, so 3 plus 1 equals 4. So this signal will be a quartet, but what will be its integration value? 2, because the actual number of hydrogens giving rise to the signal is 2. I should write H2. I just wrote I again. Okay, and then what about this one? What kind of multiplicity is this one? Singlet, right? Because there are no neighboring hydrogens, right? It only has an S and then nothing else. So it's 0 plus 1 equals 1. So it's a singlet. And then what's the integration value, though? 3, right. So it should have H3. Okay, so we've covered integration, multiplicity. There's only one more thing we need to answer this question, and that's chemical shift. What is chemical shift, and like what determines it? De-shielding, downfield or upfield, those are all true. What makes something go more downfield? If it's closer to something that's electronegative, right? So downfield is basically just a bigger number, okay? So this alpha sign is also called ppm. So a higher number, I don't know why I wrote 1, I meant to do this. A higher ppm or alpha, basically your x-axis, a higher number, which is always to the left, which is downfield, is more de-shielded, which just means that it's closer to electronegative atoms and pi bonds, and like double bonds and also triple bonds and stuff like that. Triple. I don't know how to spell. Okay. So chemical shift, meaning a higher ppm value or being more downfield, more to the left. Your signal, the whole multiplicity and integration of the whole signal having a higher ppm means that you're closer to something more electronegative. So not too bad. So that being said, between this signal and this signal, which one should have a higher ppm value? The one on the right, because it's closer to something that's more electronegative. Does that make sense? Okay. So the one that's furthest away or should have a low ppm value should be this signal, which is a triplet that has an integration value of 3. There's actually only one answer that has a triplet with an integration value of 3. Which one is that? B, right? So it has to be B because the lowest signal, the one with the lowest ppm, you only have 3 signals, and our lowest signal needs to be a triplet, which this one is, right? 3 lines, 1, 2, 3, and an integration value of 3, 3H. This one has 3 H's but 4 lines, it's a quartet. This one has 2 H's but it's a triplet, and this one has 2 H's and it's a quartet.
How would you determine between CH2 and CH3, which one's more de-shielded?
This one is technically more de-shielded. I'm sorry. Yeah, this one is going to be more de-shielded. I'm trying to think why. I think just being next to more carbons as well makes you more de-shielded. I don't think it's because it's a quartet. I think it's because it's next to a carbon, whereas this one is not. If that makes sense. What was it? No. I don't have like a super good answer as to why, but you can tell with this question because the 2H that's a quartet is the higher number, right? And then the 3H that's a singlet has a less high ppm, so it's saying that this one is more de-shielded, and the answer is B. I'm not sure why, but if you have more carbons, I think that's why it's more de-shielded, because that's the only difference between the two. And the hydrogens. Maybe it is the hydrogens. I guess you could argue that this one has more hydrogens for the dipole to act on than this one. So maybe it acts stronger on this one. Maybe that's why. I'm not sure. Any other questions, though, on integration value, multiplicity, and chemical shift? Did that make sense to everybody? Because you're going to have a decent amount of NMR questions. Even if you hate NMR, you will. So definitely be able to practice being able to determine the number of signals. That comes up a lot, and sometimes you can answer an H-NMR question just based on that. And then this one I chose specifically, though, because you needed to use everything, so that way I could go over everything. So chemical shift, multiplicity, and integration. Okay. Okay, this one. This is another H-NMR question. Okay, first thing, do we count this signal at 0? No. I don't know, I think it's called a TMS or something. Whatever it is, you don't count it. So we don't care about that one. Okay. The first thing I do when I come across an NMR question is I count my signals, because instead of going through and trying to do all your triplets and stuff of everything, a lot of times you can cross off all or half the answer choices just based off of the number of signals. So this is H-NMR, right? So we're looking at the different groups of hydrogens. So how many signals do we have on our graph? 5, right? 1, 2, 3, 4, 5 signals, right? So we're looking for something with 5 signals. Okay, so how many signals does A have? All right, let's go. Okay, we have this one. That's 1, right? That hydrogen by itself is its own area. These two groups of hydrogens are the same. Do you guys see that? They were nice in the way that they organized it because they look the same, but it could be even less obvious. But you guys, does anybody not see how those are in the same environment? So they're going to be the same signal? Okay, so they're equidistant from everything to each other, if that makes sense. Okay, and then these two are going to be the same, right? Just like the other two. That's what signal. So far we have 3 signals for this one. This carbon doesn't have any hydrogens. This carbon doesn't have any hydrogens. What about this carbon? Does it have any hydrogens? Yeah, 1, right? It only has 3 bonds, so there's a hydrogen here. A lot of people forget the hydrogens on the benzene rings. Yeah, so these 2 hydrogens are equidistant from everything, so they're a signal. These 2 hydrogens are the same signal, and then this 1 hydrogen on the end is actually its own signal because it's also just 1 space further than the last group from everything else. Does that make sense? These hydrogens are 2 spaces away from this carbon chain, whereas this hydrogen is 1, 2, 3 spaces away. Does that make sense? You're basically just looking for symmetry. Any questions?
So a benzene ring isn't just 1 signal?
No. Yeah, sometimes, like, because H-NMR is finicky, like sometimes, honestly, more realistic-y type questions will show it as 1 signal because a lot of sometimes they don't show up as well. But if you're strictly talking about concept and stuff, these hydrogens are technically equidistant apart, and they're all, this group and this group and this group would all be different. Does that make sense? So for the ACS, I would treat everything as, if it's in a different environment, it's its own signal, for sure. So this has how many signals? 1, 2, 3, 4, 5, 6, right? So that's 1 too many. Does that make sense? Okay, and then what about this? We have 1, 2, that's not a signal, 3 and 4, and then 5, right? So that one checks out. What about this one? 1, 2, 3, 4, 5, all right? And then for this one we have 1, 2, that hydrogen, 3, those hydrogens, 4, 5, 6. That one's kind of hard, but do you guys see that? Anybody not being able to pick out the number of signals? For
trouble with the rings.
with the rings? Yeah, if it helps, you can draw out the hydrogens. So we have 1 here, 1 here, 1 here, and 1 here. We don't have any right here, right, because they have 4 bonds. This hydrogen is really close to these 2 substituents, so that's going to be different than the other ones on the ring, right? So that hydrogen is its own signal. This hydrogen, oh, I'm sorry, these are their own signals, my bad. This actually has 7 signals. 1, 2, 3, 4, 5, 6, 7. Because these 2 substituents are different. So this one is closer to the the ketone, and this one is closer to the alkyl group. So those are different. So this has 7. Do you guys agree? Were you guys confused because I was wrong? That's good. That means you understand. That means you really get it. Okay. Any other questions? Okay. So we're between B and C. I drew all over them, but we can still figure it out. What can you use to decipher between B and C? Is there anything that anybody sees that stands out? The which one? Highly deshielded singlet. Yes. This signal. That signal is on the chart. Look at the chart. It literally says 10, says ppm 10, and then does anybody know what it is? Aldehyde hydrogen. Aldehyde hydrogen, that makes sense, right? And it also makes sense that it's a singlet because this neighboring carbon doesn't have any hydrogen, so this would be a singlet. Does that make sense? An aldehyde doesn't necessarily have to be a singlet if the neighboring carbon has hydrogens. But in this case, the neighboring carbon doesn't have any hydrogens, so we're going to get a singlet at ppm of 10. So ppm 10 equals aldehyde. And that's on the chart. So that's why this is supposed to be M. Oh my goodness. What was that?
If we didn't know that chart, we would have had to done multiple
Yeah, so if you didn't know the chart, multiplicity wouldn't help you, actually, because this is going to be a triplet, which you have, and this is going to be a quartet, which you have. These are your two doublets, which you have, and this would also be a singlet, which you have, and they don't give you integration values. So actually, the multiplicities add up. So to answer this question, you actually do have to know the aldehyde for this particular question. You had to know the signal. Any other questions? Okay. Oh, I like this one. I've done it in Sark and I have to write all these numbers and it's a pain, but now they're written for me, so yeah. Okay. The chemical shifts in the C-NMR, so we're going to carbon NMR. Spectrum from this compound are 15.8, 14.1, 51.8, and 170.2. Which is the correct set of chemical shifts for the carbon atoms? So, what is this asking? What was it? Yeah, ppm value, how do you shield it? It's just asking which one of these, what is the correct ppm for each one of these carbons? Okay, do you have to memorize all of the different carbon ppms to answer this question? No, how could you answer this question? What was it? Yeah, work off H-NMR. What were you saying?
I think you can cross off A and B.
Why?
Because the second carbon should be the most initiated.
Exactly. So that's how I answered this question. So I don't know any of my carbon NMR values at all. I can't even guess them. But I know that it follows the same principle as H-NMR, which is that the ppm values will be higher if a carbon is more deshielded. Just like the ppm values for H-NMR will be higher if the hydrogen is more deshielded. And by deshielded, I just mean the carbon is next to more electronegative things, right? So looking at this molecule, we see that carbon 2 is next to a double bonded oxygen, a regular oxygen, and a nitrogen, right? So it is definitely surrounded by the most electronegative things, right? So it's the most highly deshielded. So it should have the highest ppm value. Does that make sense? And they give you all the different values. So A and B, you can notice that carbon 2 doesn't have the highest ppm value. So for C and D, it does, right? So does that make sense? What's the next thing you could do? The lowest, yeah. However, I would just naturally go to the lowest. Which one should be the lowest value? 4, right? Because it's the least deshielded, or it's the furthest away from any of the electronegative atoms, right? So that's going to have the lowest value. Being next to something electronegative brings you a higher value, so not being next to it is going to give you a lower value. So carbon 4 should have the lowest value, so between C and D, which one is the answer? D, right? Because letter C, number 1 has the lowest value, and that's right connected to the oxygen, but carbon 4 should be the lowest because it's not deshielded. Does that make sense? So I feel like that question looks really intimidating, but it's actually super simple. So just keep in mind the basic concepts of H-NMR and C-NMR, electronegativity and stuff like that, and counting signals for sure, and that will help a lot. Okay, we have 10 minutes. I'm going to do the synthesis questions really fast because I don't want you guys to not get them. But can you pass around the evaluation forms, please? Thank you. Okay, wait, let me put half of them on the other side. Here, I don't know. Okay. Number 28, A, synthesis. What is the major product of this reaction sequence? What is NaNH2? Is it a what?
Acetylide.
Oh, acetylide.
Take away one nitrogen.
Yes, exactly, yeah. It's going to make a acetylide anion. It's going to take away this hydrogen and deprotonate our triple bond. if you think about it, Na always or usually dissociates to be Na plus, so you would get something that's NH2 negative, which just looks like a super strong base, right? It has a negative charge. So that base is going to deprotonate our triple bond and give us this negative anion. And then what will happen when we put a primary alkyl halide on a negative anion? Carbon coupling, yeah, we're just going to get this attacking over there and the Br leaving. So we're going to add those carbons to this side of the triple bond. And then we'll just have something like this. Okay, and then what does Lindlar's catalyst do? Does anybody remember? It reduces it, but not all the way. That's true. So it reduces it, and you get to keep the double bond. But what was special about Lindlar's catalyst? Yeah. So basically, it's the one that gives you the cis double bond. Because trans is more stable, right? But Lindlar's catalyst was the special reagent that will give you cis. So when you reduce your double bond to a triple bond, you would get cis, meaning your substituents will be versing the same way. This is trans versus the opposite way. So cis would mean that they're on the same side of the double bond, right? So Lindlar's catalyst gives you cis. So this one can't be the answer. This one doesn't have a double bond, so that can't be the answer. And now we just have to look. So this is adding via some carbocation rearrangement, right? It's not adding directly to where the Br is. But this is when you have a primary alkyl halide and a strong base, what kind of a reaction is that? SN2, right? It happens all in one step. So you don't get the carbocation rearrangement. So you would get A. Does that make sense? And even if you didn't remember SN2 and all that primary alkyl halide stuff, just try and think back to like when you were doing enolates this chapter, right? And you did alkylation of the enolates, you did a primary alkyl halide. It adds right where the halide is. It doesn't have a rearrangement. Unlike something like Friedel-Crafts, where it's two steps, so you have a rearrangement. Does that make sense? And then again, it's cis, so it's A because it's Lindlar's catalyst, and that's a property of Lindlar's catalyst. Any questions? Okay. This one. I think I've tried, and you can't count the carbons on this. It doesn't help you. I don't want to do it again because there's a lot, but I think that I've tried. So let's see. So we're basically just need to add two carbon groups together and then reduce our triple bond with H2PD to give you this group. What? I'm sorry. Okay, so the question is just asking which one of these set of reactions will give you this product. And each one, you're doing basically what we just did before, which is interesting, where you're using NaNH2 to deprotonate the triple bond, and then you're adding an alkyl halide, but then you're going to reduce the triple bond. Instead of with Lindlar's catalyst, you're going to use H2PD, which reduces it all the way to just a single bond. So H2PDC is a stronger reducing agent. So instead of getting the double bond, you get the single bond. Okay. I think I just did this by numbering it. Oh my gosh. So we have 13 carbons. If I was to add this one to here, it would add right there, right? And right there. Does that make sense? But the triple bonds would get reduced. Do you guys see that? That's how I would do it. I wouldn't redraw them all because it'll take an eternity. And then I would just number them. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Oh, counting the carbons did help, right? Do you guys notice? Well, not only counting the, yeah, that's the only way I could do this, but I thought that there were the same amount of carbons, but the substituents were just in different places, which is also true, right? Because if you look, you have a methyl on carbon 4, and your methyl should be on carbon 5 and 9, but it's on 4 and 8. But also, you don't have enough carbons anyway. So, does that make sense? I didn't count, yeah, I didn't count the end one. I didn't count any of the substituents because I was just trying to use those numbers to see where the substituents should be and how many, like, on my, I don't know. I didn't count them because that's not how my brain works. But you could. It's up to you. I was just numbering them for, like, to get an idea of where everything is, basically. Okay, we're running out of time, so I'm just going to do the answer one really quick. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Right? I probably should have flipped these numbers, but it's going to end up to being the same, right? Because you're still going to get the methyl on 5 and the methyl on 9, and you're going to get the 13 that I counted. But if you numbered it differently, that's fine. It's just numbering for you to try and help you figure out where everything goes. It's just kind of like a carbon, I don't even know how to describe it. Carbon placement question? Okay, so what is the product of this reaction? Okay, I hate how this is drawn. I spent probably like 10 minutes trying to figure out what this is. But once I did, I was like, oh, this question's easy. Okay, so does anybody know what this is? Yeah, it's a malonic ester. It's just written in like, I don't know. How I figured that out, you have a CH2, so that has to have 2 different substituents, and it's this whole thing on both sides of that CH2. That's how it's written. So the CO2, CH3 is just an ester, right? CO2, CH3, and there's 2 of them, right? 2 of them, and they're flanking the CH2. So this is just a malonic ester. So that was the first hurdle. And then what does NaOMe do to a malonic ester? Deprotonates this middle carbon, right? Remember, that's from the enolate chapter. That's the most acidic hydrogens. It's going to deprotonate that one. And then what is this going to do? What does it do? Yeah, it does an SN2, so it's alkylation, right? So you would add to one side where the Br is, right? And then what's going to happen to this other side? It adds to it as well. So it's going to actually make a little ring. And I know that you guys didn't do many 3-membered rings and that you're told they're really contortionally strained, but they do kind of show up on these. So then your second step, I'm not going to draw it all out again because we're running out of time, but if you deprotonate this again, then it would reattach on this side, so you would get a triangle. Does that make sense? So you get this kind of triangle thing. And then what does H3O plus and heat do to the ester? Decarboxylation, you guys remember that? So it's going to turn these esters into carboxylic acids and then cut off 1/2. What's this reaction called? Malonic ester synthesis. Do you guys remember doing malonic ester synthesis? Yes, that's what this is. Not in kind of in disguise, but it's blatantly malonic ester synthesis. It's just you had to dialkylate it from the same alkyl halide, which I did a couple of those questions. I don't know if you guys came across them, but you can do it. So you can dialkylate it, you can alkylate the middle carbon twice, and you can do it in a ring. And then the H3O plus and the heat is just doing the decarboxylation. So the answer is A. It's just this weird triangle with a carboxylic acid attached. Does that make sense?
Wait, we're doing the CH3.
This whole side, when you do decarboxyl, so when you do H3O plus, that turns your esters into carboxylic acids, both of them. Once they're both carboxylic acids, and you decarboxylate one side, you would get this. Right? Because this becomes a carboxylic acid, so this goes away.
Yeah.
Does that make sense? So then you just have carboxylic acid and triangle. Okay. So, yeah. the last question, predict the major product of this reaction. KMNO4 is going to make this into a carboxylic acid, right? Then we're going to brominate it. Carboxylic acids are deactivators, so you're going to brominate it in the meta position, right? And then SOCl2 is going to turn your carboxylic acid into an acid chloride. And then you're going to do a substitution with your primary amine to get an amide. So it's this one, right? We get the carboxylic acid, then we get the meta position bromine, then the carboxylic acid is going to end up becoming an amide because we used the SOCl2 and then we use the amine. You guys remember that? You just did carboxylic acid, so hopefully that's not too bad. Okay, we are out of time.
What's the number?
The number?
Yeah, I don't know. It says please go on the number.